Okay, so section 5, similar figures. I gave you this nice little diagram. It says for two polygons to be similar, corresponding angles must have equal measures. So corresponding means in the same relative position. So if you look here, these triangles are not in the same position, but it says ABC is similar. This means similar to EFG. So that means that A goes with E and B goes with F. So the order in which a shape is named is very important, okay? And so when this happens, we can pick out which angles go together. So for example, the angle that was at E matches the angle that was at A, the angle that was at F matches the angle that was at B, and then the right angles go together, okay? So the angles in similar figures are going to be equal because you can't make something just bigger but similar without changing and change the angle at the same time. And then it says the ratio of the lengths of the corresponding, so corresponding just means sides that go together, must be proportional. So this one here, it has AB is to EF as BC is to FG, and AC is proportional to EG. And this goes along with their names too, okay? So when we are matching similar figures, like this one says, which rectangles are similar? So they might all look like they're very similar to each other, but they're not based on the ratios of the corresponding sides. So let's just break this down two at a time. So let's do J and K. And sometimes like this one is fairly straightforward. So notice that the long side is doubled, right? What about the short side? Doubled. Okay. Let's check the other one though. So this one is more than doubled, and this one is more than doubled. So we can't be certain until we simplify them, okay? So example, you can do 5 is to 12 as 2 is to 5. Use your cross products. 2 times 12 is 24. 5 times 5 is 25. Are they the same?
No.
No, but they're similar. So all that I did is I went 5 is to 12 as 2 is to 5. Both these measurements came from this rectangle. Both these measurements came from this rectangle. 5 and 12 went together, and 2 and 5 went together. So I checked to see if they were similar. So far not. Okay, so let's check my other two just to be certain that we are excluding the right ones. So this one, I could do 10 to 12. So 10 is to 12 as 4 is to 5. Use cross products. What's 10 times 5? 50. What's 12 times 4?
48.
48. Are they the same?
No.
No, but they're really close, but they're not quite. So what we did is we just went through all of the ones and we ruled out which ones were similar and which ones were not. The two that are similar ended up being the ones that were the most obvious. Okay, the same thing, if I doubled the long side, I doubled the short side. Sometimes they're not obvious. Okay. So we have another example over here. They gave us the name. Sometimes they don't give you the name. So ABC is similar to triangle DEF. So I always try to match up the sides, and sometimes it's nice to do these with like a color. So like AB goes with DE. So I'm going to do I should just do them both purple, sorry. So those two sides to go together, and then BC goes with EF. So EF is the long side, BC is the long side. And then I'm just going to leave that third one blank. Okay. So it wants us to, on this particular one, I think we actually need to find the missing length, because if you notice, we don't have the missing length. Okay? So, if I were comparing sides, I'm going to do the purple. So 6 is to 5. 6 is to 5. Oh, sorry. Oops. I'm going to do 6 is to x. We'll find the side of that purple one. And then we have to use the non-colored sides. So 10 is to 5. So then we would do 5 times 6, which is 30, divided by 10, which is 3. And that's our answer. So this side, we were solving for the purple side, and that ended up being 3. You probably could have done that one in your head as well, just knowing that like 5 is half of 10, so that means that 3 would be half of 6. Okay? So some of them are really obvious. Okay, so which triangles are similar in this case? Like I said, if they give you 3, it's probably the hardest one because you have to kind of match up 2, and then 2, and then 2. So we're going to have 3 different situations. Let's set them all up first. Okay, now in this case, oh, I do have 3 different lengths, so I have to do all 3. So 8 is to 16. 9.5 is to 17. And then 7 is to 13.5. Okay, I didn't set up a proportion, I just set up them all, and we're going to see if they're equal. Well, I'll show you. Okay, then my next one I'm going to set up, I'm going to do the little triangle over here and the bigger triangle. So this one was these two. Then I'm going to do the little triangle and the bigger triangle. So 8 is to 20, as 9.5 is to 23.75, and a 7 is to 17.5. It's just 17.5. That bottom one. So I did 8 is to 20, 9.5 is to 23.75, and 7 is to 17.5. So I just, the ratio. Okay, then the last one here, I have 16 is with 20, 17 is with 23.75, and then my last one, my bottom side here is 13.5 to 17.5. So I'm going to show you the easiest way to do this. So what I did is I set up a ratio of side to side, side to side, side to side with 3 different pairs because we don't know which ones are similar. Is it going to be these two? Is it going to be these two? Or is it going to be those two? So there's 3 different choices. Now, the reason why I'm doing it like this is because these are not very pretty numbers. Would you agree with me? Okay, except for there's like in the pink one, what is 8/16 equal to? 1/2. Okay, so this equals 1/2. So if these were similar, these would also have to be half, and this would have to be a half. Now the easiest way to do this on a calculator is to divide them all. Okay, so like for example, if I did 8 divided by 16, I'm going to get 0.5. Okay. What about 9.5 divided by 17? Do I get 0.5?
Yeah.
Exactly 0.5?
No.
No. Okay, let's just do the last one for interest. 13.5. Do I get the same number? No. So because these were all this different, they are not equal to each other. Like if you picture it just like a fraction, they're not equal. So then that one is not. Okay, so let's check the next one. If I take 8 divided by 20, Do you see I get 0.4? Okay, so this one equals 0.4. Let's take 9.5 divided by 23.75. Ooh, do you see I get 0.4? That's a good sign. What'd you say? Ooh, look at that. So I just happened to find the two from opposite sides. Ended up all the ratios were the same. So that means so far that these two are equal. Let's check our last one. That's these two. Okay. So 16 divided by 20, and you guys get to use the calculator, so this is going to make your life a little bit easier. And then 17 divided by 23.5. Oh, see, we're already off. Check last one, 13.5 divided by 17.5. Oops, I times it. That changes things. Divided by. Anyways, it's not correct. So these ones are not equal to each other. So the two that are similar are the ones that have the same ratio. So if you took 20 and times it by 0.4, you would get 8. If you did 23.75 times 0.4, you get 9.5. And if you took 17.5 times 0.4, you get 17. So they have the same multiplier to produce a similar shape. Okay? Okay. So the next one is finding missing measures in similar figures. So if you're finding a missing measure, we're going to use proportions. I like to have you guys draw a little picture. So it says a picture is 10 inches wide and 8 inches tall. So I would literally draw. Okay. 10 inches wide and 8 inches tall. Okay. To display the picture on a web page, the picture must be reduced. What does reduced mean? Smaller. It does mean simplified when we're talking about fractions. When we're talking about an object, we're making it smaller. We're going to make it 3.5 inches tall. And we don't know how wide. Okay, so pretty simple here. Now we're going to set up a proportion. We're going to be looking for this other side. So if I just do with my 10, so 10 is to x. Wide goes with wide, right, Leslie? And then the tall goes with 3.5. And if you want, you can always throw words on here so you know where to put things. And then when we solve, we take the two numbers that are across from each other. Excuse me. And divide by the odd guy out. So I get 4.375. I don't think it says to round at all, so just leave it. And then our label is inches. And then just make sure your answer makes logical sense. Was the first photo or the first picture wider than it was tall? Yes. So was that the case for the second one? It was. 4.3 is wider than 3.5.
So we're doing what we did in section 4.
Yeah, we're applying proportions. Okay, the next one. A picture is 10 inches tall and 14 wide. Similar thing. 14 inches wide. 10 inches tall. It's scaled to 1.5 inches tall and displayed on a web page. So now it's only going to be 1.5 inches tall. And we want to know how wide is it going to be. Why don't you guys take a second and try to set up that proportion? Okay, if you set up the proportion, maybe you did 14 wide with x, we don't know. You could have done the 10 by 1.5 the same, like I'll set it up both ways. Okay, and then on the bottom I'd have 10 and 1.5. And then on this one, the bottom would have to be 14 and x. It doesn't matter, as long as you put the wide with the wide and the tall with the tall, and the wide with the wide and the tall with the tall, and then you did 14 and 10 came from rectangle A, and 1.5 and x came from rectangle B, you're good to go. So then we do the calculation, 1.5 times 14, 21, 21 divided by 10 is 2.1. 2.1 inches tall.
Why?
Oh, you're right. Thanks. Does that make sense? Is it wider than it is tall? And it should be, so it's good.
Did the x go under the 14?
Nope. Not in the way that I set it up. Proportions can technically, you could set them up in 4 different ways. Every proportion.
So if I did 14 over x and 10 over 1.5?
That's okay. Yep, as long as whichever way you look at it, like the 14 and the x have to go together. If they go together sideways or up and down, it's okay, as long as the other ones also go the same way. Yep. Okay, the next one. A souvenir model of the pyramid over the entrance of the Louvre in Paris has faces in the shape of a triangle. Okay, so they're kind of giving you some extra information. Do you really care that it's a, souvenir, blah, blah, blah? No, but what shape is it? It's a triangle. 2 sides are 4 inches long and the base is 5.1 inches long. So this is the souvenir. So we have this little souvenir and each side is 4, but the base is 5.1. And then it says on the actual pyramid, so this is the real deal. Obviously, I just am doing an example. Each triangular face has 2 sides that are 27.8 meters long. What is the length of the base? And when we're talking about triangles, the bases are usually what's resting on the ground there. These 2 sides are equal. So the souvenir is made, we're going to say it's made to scale, and that's how we're going to use proportions to solve it. So if I were setting this problem up, I would do 4 is to 27.8. And then the base, the 5.1, is equal to we don't know. So these 2 measurements come from my souvenir. The other 2 measurements are going to be from my actual triangle, pyramid. So I do 5.1 times 27.8 divided by 4. And this distance then would be 35.445 meters. Does that seem accurate? Was the 5.1 longer than the sides? The base is longer than the sides? It was, which is the case for this one too. So you kind of want to double check to make sure that makes sense. Okay, letter F. A t-shirt design includes an isosceles triangle. So even if you were reading this question on a test and you're like, I don't know what an isosceles triangle is, what do they tell you? The side lengths are 4.5, 4.5, and 6. So an isosceles just means that 2 sides are equal, okay? So I have 4.5 and 4.5, and then my base is 6. An advertisement shown the enlarged version of the triangle, 2 sides that are each 3 feet long. So remember, this is in inches, and this is in, the other one's going to be in feet. 2 sides are each 3 was the length of the 3rd side. You don't have to do any dimensional analysis when we're just using proportions. So 4.5 is to 3. As 6 inches is to how many feet? 3 times 6 is 18. Divided by 4.5, it'll give you 4.